my latest news in this area is the measure which I don't think that anybody really knows, but which I think is relatively consistent. And then some philosophical discussions. So using this possibility that we might have different collections of universes, actually, as the same universe divided into different parts, then we have a problem how to estimate the probabilities. So this was the work by several authors with great names, and they, when they measured the probability, they just said that given the constants, then is it for you probable to live in the universe with given constants, but not taking into account much about the volume and how much it grows and stuff. Okay, so they found that it is not impossible to live in a state with the present value of the cosmological constant, maybe not extremely likely, but not unlikely as well. So that may be then not a problem which we want to spend our life as a physicist to concentrate when we have real problems to solve. Nevertheless, to make a complete judgment, you need different approaches to estimate this probability. And there were several different probability measures, starting from the simplest one. You just consider a given point, and you see what happened with this point during quantum fluctuations in the early universe. It jumps, it experiences some Brownian motion, and then what is the typical fate of a given point due to this Brownian motion? What would be your evaluation of probability doing something? Another, and this approach would not be very problematic. These consequences might be, but it would be a nice approach to work. However, it ignores the fact that our universe has volume growing during inflation. So some benefits of inflation kind of are not taken into account in this approach. There is another approach was to take into account this volume of the universe, and there were several different probability measures suggested to it, and some of them are still used at the present moment, and some are not used but also not known. It seemed to have some advantages with respect to first one, because it does not depend on the initial conditions. Our universe kind of enter to the stationary state, which does not depend from the way how the universe started. And I will describe this situation right now. And we were working on it, and everything was nice, but then there was suddenly the problem of Boltzmann brains, that if we are considering this infinite number of universes, then in some of these universes, some human kind of like beings could be created from quantum fluctuations, and you may compare the probability for us to be Boltzmann brains and the whole world is an illusion, and we start comparing. And this was one way to see that some of the measures which were proposed before did not make much sense. This is one of the examples. Just to illustrate the problems which may appear in this context. So suppose that originally our universe was started in the high energy state, in a metastable vacuum state here, okay, number 3. And then this tunneling may bring it down and bring it down to the right side of the potential, to the left side of potential. After that, it had a long stage of slow roll inflation, which increased the volume of the universe exponentially. And after that, it falls down to the minimum, and then it lives there. So this is very oversimplified model of what really may happen in the universe, but this can be used as an example illustrating the problems which may happen here. So this is this was all for me initiated all these kind of studies with this people like that. When we studied the probability distributions taking into account volume, stochastic motion of the scalar field in the expanding universe. And we found that depending on the choice of time, whether we use the time which is ticking time, or whether we use the distance between galaxies as a time, which is okay. Okay, we had different probability distributions, and this can be explained on this example here. I will not go to details. It's better to go to well, to just my paper on that, describing these probabilities, how you have a probability to tunnel, and this probability goes with probability gamma 3, 4. Then you are rewarded exponentially by the volume, which you get here if you are volume measured. Then you fall down and just wait. And you may do the same here, rewarded here, and a fall down here. But there was something else here, that initially you started at the height of this potential. And this part of the universe where you are sitting here high, it continues expanding. It expands with very large Hubble constant in this huge vacuum. So it produces lots and lots of pieces of space of the universe. And from each of these parts, you may produce bubbles, and you may fall down here and here. And the result of studying stochastic effects, stochastic motion in this background, or just growth of different parts of the volume, what strange thing that you find is that the total volume of all of these parts, the parts that are falling to the left minimum and the parts falling to the right minimum, the total volume of each of them grow exponentially, like e to the ht, if you use t like normal ticking time, or they are this parameter beta, if it is just e foldings of inflation, then there will be there will be just h to the 0th degree. So there is some choice of time somehow determines you the final answer, which is shown here at the bottom of the slide. And then when you see it, you understand how, if your physical results depend on choice of time, this is different. Look, what was strange there, and what was the motivation in developing this measure, is that you can choose anytime you want, but if you take into account this exponential production of new and new parts, you have some parts falling to the right and some parts falling to the left. And the number of these parts falling to the right and to the left continue growing exponentially with this exponent e to the h to the degree beta t, with the Hubble not related to the present stage of expansion of the universe, but forever. And they continue and continue and continue. And if I decide to compare the number of these, the answer which is written here, it does not depend on the cosmological time. It depends only on the difference between time when you fall to the right minimum or you will fall to the left minimum. So this was significant. Our universe becomes stationary. This stationary regime, this is for us like was emotional shock, that you do not need to think about the origin of the universe, that this is first time when the universe emerged, because the whole process is a stationary process. Okay, the probabilities does not depend on the time of the Big Bang. Okay, this is related to this tree of the universe, which I was trying to show. But the fact that it depends on its delta t means that the answer does not depend on the time, but comparison between two different processes depends on this delta t here. That's it depends on the choice of the time. It depends on this parameter beta. So this means that the result is gauge non-invariant. You want to have a gauge invariant, does not depend. This is just a gauge which you use. Choice of time is just, well, your choice. Okay, so when your results depend on the way how you choose the time, you know that something is wrong. So we realized that something is wrong, but not immediately. The major push was by the paper by Max Tegmark, who just applied this naive calculation with probability measure related to the total volume. And he found that when we will take these things into account, really we will find out that the question, in which kind of universe it is most probable for us to find ourselves. And he found that it is absolutely colossally more probable, exponentially more probable for us to live in the universe not with the temperature 2.7 Kelvin, but much more probable to live in the universe with 100 Kelvin, and even much more probable to live in the universe with 1000 Kelvin, which means the main prediction of it that we must live in hell. And that was something really emotionally damaging in it. So that's the way how I start thinking about what exactly was wrong with the probability of measure we developed at that time. Okay. And at that time, many other people developed their own probability measures of probability. And each of these measures were so complicated that different people, Busso, Vilenkin, me, sometimes it was impossible to read everything which everyone have written, where there were several different flows of suggestions, and it still remains at the moment. So this is my discussion of one possible flow of thought, which I found much better than at least what was previously available. Because this was something which was suggested by Tegmark. If you read his suggestion, he say that maybe instead of comparing everything at a given time, you must compare processes, and then compare processes the moment when they started. And here is the analogy. Suppose you planted trees, and some trees produce red apples and some trees produce green apples. But red trees start giving apples 5 years after you planted them, and the trees producing green apple start producing apples 10 years after you planted them. After that, they produce apples, and you start comparing them. It's the same like when you have this inflationary self-reproducing universe, you have stationary process, they continue producing different universes, red and green. But this production starts at different time for red universe and for green universe. And it is incorrect to compare red apples with green what? At the time t for 5, whatever. At the time when first red apple was produced, there was no green apples. You see that green apples and red apples, they grow with the same speed at the time when they start, being produced. And that's exactly what happens in this picture, which I've shown you. Let me return back to the picture. So you have this picture. You fall down to the right, and then you roll from point 2 to point 1. It is similar to, you have a package coming from Amazon, but it goes such that the delivery takes a lot of time from 2 to 1. Package is already there, but it is not yet delivered to the minimum to the right. And package which fall down to the point 4, it rewarded. The total number of these packages grows exponentially when it rolls from 4 to 5, but they are not delivered yet to the point 5. But this delay in the delivery is much shorter to the left part than to the right part. But this is the same packages. It's just like with these apples and trees. And once they delivered for the first time to the right, and delivered for the first time to the left. This is the time when you start comparing packages. So then starting from this moment, you have stationarity. Stationarity is guaranteed by existence of these further while standing on the top of the hill and sending new and new and new packages downstairs. Okay, so this ensures you stationarity of the process, but the process becomes stationary for the left part first, and it becomes stationary for the right part later. So it is wrong to compare the left and right at the same time, because then you compare the processes such that one is already stationary and another one isn't. Then what happens if we start comparing them at the same time? Well, if we just ignore this one, once you have a package, you already count is there, and just volume of the package grows when it grows from move from point 2 to 1 and from 4 to 3 normally, but the packages are already in the mail. Okay, and once you calculate that, magically this red factor completely disappears, and what you will have in the result, you have gauge invariant measure, which tells you that yes, you are punished if probability to tunnel from 3 to 2 is small. You are rewarded if you spend lots of time rolling from 2 to 1, and that gives you the physical result just because you start using concept of stationarity correctly. So what was wrong here? Exactly the same thing, like, well, exactly, not exactly, but the analogy may be right. When we are talking about special theory of relativity, we are talking about simultaneity as something obvious, something like does not require procedure. Similarly, when we developed the first volume-weighted measure, we took it like that. Okay, let's make an experiment with that. We did not even originally plan it. Was like year 1996 or something. We didn't even think about really seriously using it as a measure, because we have seen that we are getting non-gauge invariant results. But well, okay, so it's a lot of interesting mathematics there. Now, when we start using it for obtaining some results, then we must be careful by defining what means stationarity. We say that you have a stationary regime, but the stationary regime for different type of processes reached at different times. Now, when we start comparing processes at the time when they begin, suddenly this gauge non-invariance disappears. Now, this is a simple model. This is very basic. And then there was a paper by Busa and collaborators, which say, no, if you take into account quantum fluctuations and whatever, then things will be different. And then we spent some time working on it by together with two talented students of Vilyankin, Manchurian, and Vinitsky, and we have shown that no, everything is normal, at least to all models which we could study. No, these quantum fluctuations do not change the result, and there is no Boltzmann-Brain problem there. So you have a situation where we solve all problems which presently exist with these measures. There possibly one problem remains. And in this case, I will just return back and point at this. Okay, so this is on this basic model, we have seen that here some intuition which we wanted to have from the expansion of the volume of the universe being rewarded by this exponent 3 n to 1. So the volume growth of volume, when you grow from 0.2 to 1, you take this reward into account. And then sometimes this reward may become too strong, because changing some parameters may change this reward exponentially large, and then it will suppress some relative probabilities of different processes. So it was called by Vilyankin Q problem. Okay, so when we studied it later, we found that it's actually a very model-dependent situation, and sometimes this problem, Q problem, really doesn't exist. So it's, first of all, it is model-dependent. It doesn't exist for every set of models, but it's just like that. And second, when we're looking at this formulation of measure, we wanted to get a benefit from expanding beyond these 60 foldings. Okay, like million foldings will give you even greater volume. However, honestly, anthropically, the only thing that you want to have is a nice piece of space of a size greater than the part of the universe right now. So maybe one should not really volume weight up to infinity, because you are not additionally rewarded by producing parts of the universe which are beyond the reach. Okay, if you want to have local homogeneity of the universe, local homogeneity can be achieved by having 60 foldings, maybe 65, whatever. So then probably some more intelligent version of the measure, which makes some soft cut at this number of foldings, will totally avoid this Q problem. But independently of that, when I studied this in application to some particular models, I found that this is a model-dependent problem. For some of the models, this problem doesn't exist. And if not, then we have a solution of the problem. Okay, so now I'm going to a totally philosophical part, because of mathematical part for me ended at this time. Is it physics or metaphysics? Because when it was suggested, even those string theorists who later joined this investigation pointed fingers at me and saying, "Oh, you are the worst." Okay, because it was really unacceptable to think about laws of physics which they want to find, and just like it is just a luck or whatever, or anthropic, and then gradually they start taking it more and more and more seriously. But nevertheless, is it really metaphysics cannot be experimentally tested? So the question is, can we test the multiverse theory? And the standard statement, which you can find quite often in the popular literature, everybody just repeated that it's impossible to test it, because these different parts of the multiverse, they're far away. Since I never can travel there, I can never test it. It cannot be tested, whatever. There is an issue with Popper. I cannot produce this universe in the laboratory, and because of that, I can just, well, reproduce what will happen, some stuff like that. And in my opinion, this this theory have already been tested. And in which sense? And this is the sense. In addition to this reproducibility test, which is often, with reference to Popper, applied to physics, there are some other tests which, well, every day is used by people in the court. It's completely different test. And that is the, well, great philosopher, which shown here, used in his novels. When you have eliminated the impossible, whatever remains, however improbable, must be the truth. So what you do, if you have some explanation of what happens, and you do not have any alternative explanation, then you take this one explanation very, very seriously. Sometimes you just, well, send the people to death, despite the fact that you cannot reproduce it. Like example which I sometimes use, for example, somebody, well, is suspected to have killed his wife, and you do not make another experiment, give him another wife and another knife, and see what happens in this new experiment. But instead of that, they just try to exclude all other reasonable explanation of what is seen here. And what do I have right now here? Well, we try to solve a cosmological constant really for decades. And first we try to prove that it is zero. Then we try to explain that maybe it is non-zero, but why? Because this was this 98. It was totally crazy. It's much more complicated to explain non-zero at the level 10 to the minus 120 rather than zero, which may be zero because of symmetry. And when nothing worked, and then you have one explanation, you just do not ignore it. Now, there is another problem. Why proton mass is similar to the neutron mass with accuracy better than 1%? Well, you know that if proton mass would be 1% heavier, then protons would decay, and you will have a universe where only neutron stars will exist, nothing to build people from. And if neutron would be heavier than a proton by 1%, then all neutrons would decay, and you have only protons and decay, no chemistry, no life. What would be with the dimensionality of space? Why do we live in three-dimensional space? Oh, okay, nobody cares. But string theory tells you that the space is 10-dimensional, so potentially it could be 6-dimensional, it could be 5-dimensional. Why it is 3-dimensional? Well, Paul Ehrenfest in 1917 explained that life as we know it could not develop in 4 or 5-dimensional space because planetary systems there would be unstable and fly away or fall down on the sun. Just simple mechanics. Okay, nobody in the institute where he worked know his work. I was at this institute, wonderful place, portraits of Ehrenfest at every corner. His house is there like a museum. And when I told him, do you know that he explained in 1917 why our universe is three-dimensional? No, nobody knew about this because it was nonsense, because it was unscientific. Now you have a possibility, you have a science, string theory or any other theory with compactification, and then it allows you to have not only three-dimensional but four-dimensional universes, but you know that you cannot live there, and you know that inflation can reproduce you different parts of the universe with different properties, including dimensionality. Then you know that you can live, we can live, only in the parts of the universe which are three-dimensional, so you don't worry about this problem. So that was impossible until all of these recent developments, but became possible now. And as I said, nobody in his institute knew that he, had this paper. In this respect, and I am finishing right now, it's totally philosophical, but it's just like an example how one can use this. Albert Einstein said that most incomprehensible thing about the universe is that it's comprehensible. And then another one, a mathematician, said that unreasonable efficiency of mathematical and science is a gift we neither understand nor deserve. So all these wonderful people, they all were confused by the fact that what is this about this unreasonable effectiveness? And then the reason is the following. They were puzzled because if the universe is everywhere the same, no choice, then the fact that it obeys so many different laws that we can discover, remember, and use, it is just a miracle. And it is undeserved gift of God to physicists and mathematicians or whatever. So that is why we neither understand nor deserve, as Wigner said. But in the context of inflationary multiverse, this problem disappears because the laws of mathematics and physics are efficient only if they allow us to make reliable predictions. The possibility to make reliable predictions is necessary for our survival, and they're part of our game of evolution. And there are some parts of the multiverse where information processing is inefficient. We cannot live there. For example, we cannot live at the Planck density. Everything that you create at the moment during the Planckian time will be completely erased. We cannot live in anti-de Sitter space, which rapidly collapses. Again, we cannot use any information which we have. One way or another, we can live only in this parts of the multiverse where stable enough, which allows stable information processing and reliable predictions. And that is why physicists and mathematicians, they can live only in the part of the multiverse where physics and mathematics are efficient. Otherwise, no predictions, no winning a game of evolution. And as a result, what I should say, that physicists can live only in those parts of the universe where mathematics is efficient and the universe is comprehensible. So I wanted to finish with that. This is, not a statement which can be measured with any this or that probability measure. This just shows you that with these new concepts which became available to us relatively recently, there are some other ways of thinking about our world which was previously unavailable, and now we must learn how to use them correctly. But we must use these opportunities instead of just ignore them. Thank you.